Welcome to qnawire.
Question, we have a Z particle. This is a Greek letter for Z. It's like 3 lines. The particle at rest decays into a lambda particle and a particle. We want to find the total kinetic energy decay products. So we're only looking for the kinetic energy, which is the energy change that is induced by the mass difference in this reaction. So in order to find this, we can find the change of mass. Delta M C squared equals the mass of Z C squared minus the mass of lambda C squared minus the mass of pi C squared. So the first case, the first particle has a mass of 1321 MeV. Lambda has 1116 MeV. Final has 139.6 MeV. The mass difference is 65.4 MeV, and this difference equivalent energy is going to be shown as the kinetic energy of the final product. And then we need to look at part B. Part B is a little bit more tricky. Part B asks us what fraction of the energy is carried off by each particle. So this is a momentum question. The momentum is conserved in this case, but at the same time we want to use a relativistic expression for momentum and energy. So the relativistic expression, we have previously the energy is the rest energy of the particle. Afterwards, the energy of the particle, but because moving, we need to use the relativistic expression for this. So it has rest mass and the rest energy in addition to the kinetic energy. So this is going to be our expression. And here I am that they have momentum. Pi and lambda particle share the same p. And this is because momentum is conserved. And momentum was 0 before the reaction, so momentum must be 0 after the reaction. So this is the equation we're going to have. We can rearrange it and square both sides. And if we square both sides, we are going to have C force. I move this to the left and against I am going to have plus square c to the fourth plus p squared c squared minus times c squared energy lambda equals mass of pi squared c to the fourth plus p squared c squared, and p squared c squared over here actuals. So we will be able to find the amount of energy carried by the lambda particle. Q times mass of Z. With this amount of energy, we will be able, this is a total energy, so we can find the kinetic energy because kinetic energy is equal to total energy minus the rest. So similarly, we can find all the other numbers with the same method. This is a kinetic energy, and again, we have all these numbers. We know what the mass of Z is, we know what the mass of lambda is, we know what the mass is. If we this to this equation, we will get that the kinetic energy carried by lambda is 8.5 eV. So this is our equation. The equation we can have the pi, and the equation of pi can be defined similarly. You don't even have to get this equation. You can just write it down because it is symmetric. So square. It is all the same except that in this case we're taking the of the lambda particle and adding the mass of the pi particle. And this one we're subtracting the rest mass of pi. So again, look at this equation. Looks pretty much the same as this one because they are symmetric. And again, we plug in all the numbers and we get that we have a kinetic energy of 56.9 MeV. Most of the kinetic energy is by this pion particle because it is much lighter.